Can get started. So we're happy to have our third speaker of the day, Shvydkoy from University of Illinois at Chicago. He's going to be telling us about hypercoercive dynamics of Fokker-Planck alignment equations. Thanks very much.
Okay, so thanks organizers, first of all, for putting together a great effort despite the difficult times. Hopefully next time it will be in person, we'll see. So I have to apologize to those who, I gave a similar talk recently at the SciEM PDE seminar. It was more like maybe a colloquium style, but apologies to those who attended those because there will be a lot of overlap, of course, with the current one. So I'm going to talk about hypercoercivity of some equations that arise in kinetic equations that arise in collective behavior models. And not only that, I would like to kind of gradually motivate the questions. And so we will naturally look at various other levels of description in the context of this emergence problem. So what we're dealing with is a system of agents which belong to some domain which we call environment in collective behavior. And just to avoid issues with the boundaries, I'm going to assume that it's either open space or a torus. And in fact, most of the time I will be restricted to the torus because I need compact seconds to explain some phenomena. So the system is assumed to have some kind of self-organization dynamics. So it has some communication between the agents built into the forces that govern the evolution. And possibly some external forces like confinement or stochastic forces will be also in our interest. So recently, the problem of so-called emergence has been brought into the kind of the realm of mathematical analysis. In a very rapid fashion. It has existed mostly, unfortunately, mostly in applied literature before. And just to explain, emergence means that a phenomenon of formation of some cohesive structures resulting from local interactions. So if we have a system with global interactions and we know that each agents communicate with every other agents, then probably won't be surprising that they would agree on something and arrive at a consensus, right? But what if each agent has only a local range of communication, can talk to only maybe finitely many of agents around it? Will we see any formation of global cohesive structures, and under what conditions? So that is the kind of, in the very general terms, the problem of emergence. Okay, so of course, a couple of days ago, Trevor Leslie gave a good talk, and I think it was a good introduction into what, into various moving parts here. So I will just brush through relatively quickly. These things, of course, arise in many different contexts, and mostly in biological. Of course, if you look at the flock of birds or school of fish, you see formations of aligned patches of these animals. There's swarming behavior of ants. This is kind of out of the context, but still. But also things like decentralized control of robots or humans, okay? And technological applications to cosmological navigation and all of this. So there are really a lot of application of this problem. So again, I'm kind of repeating Trevor at this point. So what we mean by there are many emergent phenomena, of course. So one can see patterns in forming in biological systems, like milling patterns of schools of fish. Here we're going to be looking at more like a local emergence, which means that there is some kind of consensus of vectors, right? So alignment, we call it alignment. Alignment means that all velocity vectors in your system converge to a common vector. And by the way, by velocity, I mean just the, it doesn't really, not necessarily means the physical velocity, okay? It really depends on the context. It can be opinion, for example, in opinion dynamics. Now, by flocking, we mean that the agents will remain within a confined radius for all time, although the flock can travel, of course, with some momentum. And strong flocking means that as time goes by, there is some kind of crystallization of the flock happening. So there is no further permutation between agents. They kind of they form a graph which moves in a parallel fashion. Okay, so there are a lot of interesting models, of course, to which describe various phenomena. One of the classical model is the V-shaped model of this kind of special averaging protocol included in it. Unfortunately, so what it does is basically it averages velocities in a local neighborhood around each agent, and it normalizes the velocity. So it kind of forces the velocities to be of the same length at least, right? And so it becomes the question of whether they will direct in the same direction as time goes by. That's one very hard to analyze because it's singular from the point of view of well-posedness as an ODE system. So people study it as discretely in time. But nevertheless, it's very popular in applied literature and has seen a lot of success. There's a huge class of environmental averaging model of first order, such as Haxelman-Krause model of opinion dynamics. Also, it's a local model. It's just saying that these states, PJs, are averaged according to a given protocol in the local neighborhood. And the question is whether you arrive at consensus as time goes by. Another very, very well studied from actually analytical point of view, a lot of people doing the Kuramoto synchronization model, which arises in cardiac cell synchronization, or maybe even cricket chirping. There's a paper that provided compelling evidence that this model is good to model the synchronization of crickets, right, as they chirp in your backyard. Recently, a very popular class of models was discovered by Cooker and Smale, and they're popular because of their simplicity and flexibility. So there's this communication protocol that's included in the model. It basically, the model is a typical alignment model. So your velocities are trying to mimic the velocities around the neighborhood of your given agent. However, the strengths of that communication is regulated by kernel, which depends on the Euclidean distance between the agents. So it's a very natural model actually to study. And this kernel phi is assumed to be non-degenerate, monotone, radial, and decaying. So appears in a whole bunch of applications. And the multi-scaling version of this Cooker-Smale model appeared in 2011 by Moch and Tadmor, which included this adaptive averaging. So you're not averaging just by number of agents, but you're averaging by the mass around the agents. Okay, so the sufficiently strong global communication implies unconditional alignment. And that's kind of not surprising, because if you already have, if agents communicate, if they have a capability to communicate at the long range, they will agree on something eventually. And one can actually quantify how much communication is needed to achieve alignment. And that's the original theorem of Cooker and Smale. So they postulated that the communication kernel is power law. And if that power law is non-integrable, so if the exponent is less than 1, then the flock will align exponentially fast. So although the agents may have a transient expansion, eventually the tails are still too heavy. Tails of communications are still heavy enough to ensure the slowdown of that expansion, and eventually the flock will remain confined, and the alignment will ensue. So after several iteration, this result was improved and has achieved its final and sharp form. So as long as you have this non-integrability condition on the kernel, then the flock will align exponentially fast. In fact, in our work with Dithert, we even removed the positivity assumption on the kernel, so it can be degenerate. Okay. So what about local communication, which is kind of what we are trying to understand? Well, here the problem is that it's very easy to arrive at a counterexample. So you just just set two flocks separated from each other, pointing in the opposite directions, and they will never communicate. They will never have a chance to communicate with each other if communication range is finite. So to avoid this problem, people usually require results that are known in literature, usually require propagation of connectivity. So the flock has to remain connected at all times. So it's graph connected, so I should be able to move from one agent to another along the lengths at least the communication scale. Then you can obtain similar results as in the classical Cooker-Smale case. Or one can consider the case of a compact domain like periodic torus, which essentially just kind of models the bulk of the flock, right, without any boundaries, and see whether there is some kind of recurrent dynamics in your system. So the propagation of connectivity, there are many results. One of the notable recent ones is by Morales, Pejek, and Tadmor, which says that this communication strength is sufficiently strong, and the flock is initially connected, then it will remain connected at all times. So the communication is so strong that it won't even, the flock won't even have a chance to expand. So it will kind of crystallize almost immediately. Okay, so like I mentioned, there are a lot of applications of this Cooker-Smale dynamics, even for long-range communication. So don't take me wrong that we only local communications are physical. No, they're not. So there are actually applications, like for example, this first paper here studies application to flight control, right? So this was done to facilitate the communication between a few satellites in a Darwin mission that was commissioned by European Space Agency to look for habitable planets. And the satellites had to take pictures of remote planets, but in order to do that coherently, they have to align pretty fast. So if they align very efficiently, that's not going to be fuel efficient way to do that. At the same time, if you don't align efficiently, then you will save a lot of fluid. So the question is, where is that most optimal fuel efficient parameter of the communication kernel that allows you to both save a lot of fuel and also, take sharp pictures? So that parameter was found to be 0.4. So there's really some specific engineering application of this system. So I'm not going to mention a lot of others. So here are some references. You can look them up. And one interesting recent development was the to machine learning. People actually could adapt these models to some real field data, and using machine learning, they calibrated the parameters of the kernel and to achieve a good match with the data. I'm going to mention this a little bit later as well. So when we study systems with a lot of agents, then it makes sense from statistical mechanics point of view to look into mesoscopic description. And this is typically done through various limits of various scalings. So one of the natural ones that is kind of fit with the averaging that we're assuming for the Cooker-Smale model is the mean field limit. So mean field limit means that I'm not scaling my communication kernel. It remains the same at a constant range, but I'm just pumping more agents into my system. So it's large crowd limit, and it was derived by Ha and Tadmor using formally using BBJKY hierarchy, and that was justified by Ha and Liu and Boli, Canizo, and Carrillo in a rigorous settings using Wasserstein metric. So basically proving stability of the Kruger-Smell dynamics in Wasserstein or rather Kantarovich-Rubinstein, so Wasserstein 1 metric. The interesting thing here is that both Kruger-Smell and this kinetic equation are well posed. Oh, I included the noise term here. I apologize, I'm kind of ahead of myself. But so the first thing to look at is actually just the transport, kinetic transport. And what's good about it is it's actually well posed, and the alignment can be proved under the same conditions as the Kruger-Smell theorem. In fact, in exact same way, because you just follow characteristics, and characteristics satisfy a system very similar to Kruger-Smell system. Now you go into some issues when you consider the macroscopic description. And again, Trevor did a very good introduction here, so I'm just going to brush through. So you write the system for the momenta, and you have, of course, extra Reynolds stress tensor, which you need to either model, or you have to close it using some kind of limiting hydrodynamic regime, going from kinetic to hydrodynamic equation. So there are two regimes that have been studied in this context. One is just the strong local alignment regime, was proposed by Kahn and Vasseur in just for the general Vlasov equations, and then with the alignment was proved by Figali and Kahn for on a periodic domain with the no vacuum condition on the flock. So I improved it to the open space case in for the compactly supported flocks. So there are some technicalities that you have to overcome with the vacuum condition here. And then what you arrive at is the pressureless Euler alignment system. So it's a very interesting system to study. It has been very extensively studied recently. And the reason why it's so relevant to the flocking dynamics is because it allows for a lot of collective outcomes. So any initial constant velocity with traveling wave solution for the density will give you a solution to this equation. So you may end up having a flock with arbitrary distribution of the density, and that will be a solution to the system. So plenty of collective outcomes. Another regime was proposed by Carper, Melee, and Trevisa, where you actually study the full Fokker-Planck equation, and you in a strong limit of Fokker-Planck plus so noise and local alignment, you Maxwellianize the distribution, so it converges to the local Maxwellian, which then satisfies the pressured Euler alignment system with isothermal pressure. So this system doesn't have that many collective outcomes. The only natural outcome would be the constant distribution of velocity and density. But it's still a regime, and actually a very interesting one from the point of view of probabilistic approach to this problem, which I will mention later. Okay, so I'm going to just brush through pretty quickly through some of the results that are known for the long range communication. So you can prove Kruger-Smell theorem, was done by Tadmor and Tan. You can establish threshold condition for the global well-posedness in 1D only. Unfortunately, in multi-D, it remains a pretty open problem at the moment. And the condition here is given by this conserved entropic quantity. So it's actually related to Brest-Jourdain entropy in compressible dynamics. That's why sometimes we call it entropy. but it's not exactly entropy, not the physical sense. But if that quantity is positive initially, then you're globally well posed. It's kind of like if you delete this term here and consider pure Berger's equation, then you are of course familiar with the this condition for the Berger equation. But the alignment force actually is regularizing, so you have some leeway here on the threshold. With my postdoc Daniel Lear, we developed the theory of unidirectional flux. And in that context, so these are basically compressible parallel shear flows where the velocity points in one direction, but it may depend on all spatial variables. And in that context, we discovered the existence of these Mikado solutions. So very, very relevant to convex integration and Onsager conjecture things. But that method has not been applied to Euler alignment system. So this would be very, very interesting to do actually. This picture you actually saw in Trevor's talk, so I'm not gonna say much. If your initial flow starts on a zero entropy level, so this is kind of a borderline case, then you can see aggregation phenomena as time goes to infinity. So the flow gets squeezed as it flies, and what you obtain in the end is the skeleton of the original flow. And this skeleton is actually, it's the signature of the flow. It preserves all the essential topological structure, like for example the genus of the flow. It actually also these connections that we drew here. They're not just schematic representation. These are actual up to C1 isomorphisms. These are actual pictures. So you will see that smooth reconnection of branches of flux. Now in Trevor talk, of course, he also talks about, his main purpose was to understand what happens with the negative entropy solutions. And what we expect is that we will see these structures, but only in finite time, because these solutions blow up, and they blow up in this exact fashion as we see for this borderline case as time goes to infinity. So the singular models were introduced in order to kind of compensate for the lack of to emphasize the local communication. So even though most of these results hold for the long range communications, we do want to emphasize that most of the dynamics is driven by local communication. So the way to do it is to allow for the kernel to blow up at the origin. And this, of course, introduces a lot of technical issues, right? Well-posedness, even on a discrete level. So Korea, Choi, Mook, Pezhek demonstrated that if your singularity is strong enough, has to be non-integrable, there are no collisions. So the discrete dynamic is going to be well-posed. For weakly singular kernels, when beta is less than 1, collisions are possible, but you can still develop a theory of sticky particle dynamics there. With Eitan Tadmor, we introduced super singular kernels, and our interest was driven by connection with the fractional parabolic theory, of course, because the kernel you obtain here, this is written in 1D, in ND it should be n plus alpha. The corresponding alignment operator becomes a weighted fractional Laplacian. And so you arrive at a system here, which has a lot of interesting structure. Of course, it has a parabolic regularization effect. And in fact, one can adapt the Giorgi-Nash method to prove Hölder regularization. And with further application of Konstantin-Vikol non-local maximum principle, you can kind of gauge the long-term dynamics for this problem as well in a very specific way. And independently by Do, Kiselov, Ryzhik, and Tan, they also discovered that system and applied modulus of continuity to tackle global well-posedness. So these equations were studied only in 1D. Again, in multi-D, there's only one result by me and Lear for unidirectional flux, but it's kind of mimics the one-dimensional theory. So the reason why I'm still mentioning this paper on machine learning is that they applied it to this particular model, okay? And they discovered that for singularity equal a half, it gets a 99% accuracy match with the data in 1D, and for alpha equal 1.2 in 2D. So this this result motivates compels the study of the regularity theory in multi-D. So we believe that they actually blow up, but even so, that doesn't really prevent us from studying the equation because it is really relevant. So let's go back to the local models. So we now are assuming. So let's assume just very minimal information that we can about the kernel. It's just bounded from below on a small ball. And to avoid the issues with this dispersion, we will confine ourselves to the settings of the periodic domain. Again, this is just a technical assumption. One could as well consider confining force with confining potential in the open space, but we just don't want to deal with extra forces in the equation so we just want to study the effective dynamics coming from the alignment force. Unfortunately, even on the torus, or open space with confinement for that same reason, there are counterexamples to alignment because you can sort of let one flock go along a cross section of the torus along the geodesic, for instance, and then the other agent going in the perpendicular direction, and their velocities are mutually rational. You can arrange them in such a way that they will never actually collide. So they will stay at a positive distance from each other. If that distance is is larger than the communication range, they will never talk to each other, so they will never align. In fact, these log states, they may actually appear dynamically, and I want to share with you a numerical simulation for singular local kernels done by Anil Zenginoglu back in Syscom, when Syscom existed. So how do I do that? Okay, so I'll share this screen. Okay, so I hope you can see it. Okay, so just pay attention to the window on the left. The window on the right will just show the velocity, the components of velocities. So it's not really illustrative, but the physical domain is the picture on the left. So that's the periodic torus. Okay. So the agents initially, we started with the random initial condition, and we've done a lot of these experimentation. It kind of arrives at more or less the same result. Because the kernel is singular, you can almost see that when the agents meet, they almost like behave as sticky particles, right? And that's because local communication is so strong that they will align so fast as they talk to each other that they will basically travel together without any change. So you can see there is clustering occurring, and these clusters form some kind of quasi-periodic structures. Probably if we wait long enough, they will reconnect at some point, but definitely there are a long transient period of no communication between the clusters. And that's the obstacle to alignment, of course, right? So let me go back. So how can we deal with this issue? Well, first of all, it seems like these locked states, as we call them, they are very unlikely to occur, right? Because it really needs to be very fine tuning of parameters for them to exist. So they kind of form a measure zero set of solutions, and yet they do occur, of course. But can we, for example, maybe approach this from deterministic point of view and prove that for generic initial data, we do have a global alignment? So for generic data, some of these, clusters will still reconnect at some point. This was done only in 1D in our paper with Helge Dietert, because in 1D, of course, you have a spatial limitation, right? So in 2D, that's already an open question. Now, of course, connectivity is still a remedy, right? And the question is how much connectivity do we need? I'm going to show that on the next slide. And the third one is what brings me to the main topic of this talk is the stochastic noise. So if you introduce a little bit of a noise in your discrete dynamics, then this disrupts these locked states, right? Everything kind of wiggles around. And so eventually with a high probability, the agents will start reconnecting. And so for the large crowd dynamics, the noise becomes Fokker-Planck diffusive equation. The noisy system becomes the Fokker-Planck equation, the corresponding Kolmogorov forward equation. And the alignment becomes the problem of relaxation to Maxwellian. So just to give an idea how much connectivity we need, this can be expressed in terms of lower bound on the density. So if you just write the equation for the energy, you have energy law with some dissipation coming from misalignment of the system. So as long as it's misaligned, it burns energy. And if you do the estimates here, of course, the rho is always enters as a weight in these estimates. So if you bound it from below, you get the rho squared. And then you do some analysis and you come back to the energy and you obtain this Gronall inequality. But now you have rho squared. So the rho squared has to be non-integrable in order to achieve decay of the energy. And so that means that rho, morally speaking, has to decay like square root of t, 1 over square root of t. Okay. So anything below that is treated as badly as vacuum, essentially. So one way to approach this is to try to lower the connectivity assumption, right? So we're not trying to get rid of connectivity altogether, but we just need to lower it. And one way to do it is to replace metric communication protocol, which depends only on the Euclidean distance between agents, by topological, which is in fact more natural because that's what's observed in various field studies, in particular in this star flag project by Italian researchers. There are some prototypical models that already appeared based on the nth nearest, the case what is it called? K nearest neighbor rule, right? So that each agent communicates only with a finitely many agents around. So this is kind of a discrete dynamical modeling. But for the large crowd dynamics, this topological communication can be encoded into the kernel itself. So this was done in our work with Eitan recently. And what we've postulated is that between any pair of agents, there is some kind of communication protocol through which agents communicate between each other. And the speed of propagation of the information between these two agents is inversely proportional to the mass of that communication region. Right? That's natural because if the crowd is very, very dense, then it takes longer for information to propagate. So I have to convince all the intermediaries to align in the same direction before I reach the end point. So we introduce this mass distance, right, which is just the integral of the density over the communication region, and we built it into the kernel as inversely proportional to the distance. Okay, so it's still singular communication, but now I borrow this n powers of x minus y, and I put it on this communication. One can, of course, study the whole range of models with parameters. And what one obtains is the new topological model, which presents quite a challenge from the point of view of studying the global opposedness, but it allows us to lower this lower bound on the density to a power of 1, okay, 1 over t. So you get some slow alignment, logarithmic rate, but still it's much better than 1 over square root of t, because already in 1D this is automatically holds. It's not an assumption. That's a theorem. So this lower bound can be achieved if the initial flock is non-vacuous. So we've developed regularity theory for this topological model. Unfortunately, it's very, very technical. It requires the use of para-differential calculus, quintic para-product estimates, so quite technical. But and the reason is because the density contaminates the kernel, so kernel becomes active. It depends on time and connected with the continuity. So, and so the strategy that has been adopted recently to study in this emergence dynamics and trying to avoid these locked states is through the introduction of the noise. So if you look at your basic bare bone, so to speak, alignment model, you can always add a noise, okay? In many cases, one can justify the mean field limit from the stochastically forced system to the corresponding Fokker-Planck equation. So the problem of alignment becomes the problem of long time dynamics of the solution to this Fokker-Planck alignment system. So naturally, of course, without the alignment force and maybe without these weights, communication strengths, this is a classical problem, of course, and one can actually just write down the Green's function to the linear Fokker-Planck equation, and you obtain relaxation to Maxwellian. So we're trying to prove the same thing for this nonlinear Fokker-Planck alignment model. If we can do that, if we prove that so the distribution can relaxes to Maxwellian, then we can restore the emergence through the vanishing noise limit, okay? Because Maxwellian simply converges to Dirac, okay, centered at this and at the average momentum. And this actually kind of people who do turbulence should like this kind of point of view, because that's exactly how we understand the laws of turbulence. We first take long time dynamics, so study Navier-Stokes, let's say, equation on the attractor, and then we're trying to understand the statistical limits of various statistical quantities, such as structure functions, as viscosity goes to zero, and also as the scale goes to zero as well. It kind of is like a turbulence, because initially all these locked states, all these symmetries of the initial flow will be destroyed, just like Kolmogorov predicted, but then reassembled in a different way as time goes to infinity. So that means Maxwellization. Okay, so there are many parallels with the turbulence theory, but of course it's not as complicated, because here one can see that the limited solution is just one solution, so it's we're dealing with one point attractor in a sense. But to establish this result actually is not very easy, especially in this non-linear settings. And this program had seen partial success in the beginning. In 2010, Duan Fornazier and Toscani proved for the classical Cooker-Smale alignment system, they proved relaxation in perturbative settings. So when you are already close to Maxwellian initially. And Choi in 2016 proved a similar result for local alignment model, okay, also in perturbative settings. So this in both cases, the technique was motivated by then relatively new development in collisional models such as Landau and Boltzmann by Gua, Duan, and others, and they borrowed that technique to apply to the alignment models. Now, it felt a little bit artificial because we're not really dealing with the collisional models, so we're dealing with alignment model. So it seemed that perturbative settings would be too much to assume, because you are essentially saying that your velocity is already nearly aligned, but also the distribution is almost uniform. So you stay away from, so you are assuming a lot of connectivity, right? And it will remain so by the maximum principle. So the solution will remain in the epsilon neighborhood of the Maxwellian if you start there. So this kind of motivated us in looking into improvement of this result, and the improvement comes from adaptation of the hypercursivity method of Villani. Villani and the Villette that they applied to Boltzmann equation and to Fokker-Planck, of course. But we had to choose the communication protocol in a specific way, because when you do cursivity estimates, the classical Fokker-Planck part of the equation will interact with the alignment term in a special way. And you have to kind of tailor fit the alignment in such a way that this relationship between the classical part and the alignment part is they're not fighting each other. It should be in symbiosis. So mycorrhizal relationship, if you want. Now our communication protocol is based on what's called the Favre filtration, which people in compressible turbulence are familiar with. This is a special modification of the velocity with the density pre-weighted procedure. So just like so, my notation here is rho phi is phi convolution rho. Okay, so lower index phi means convolution. The corresponding, if you just keep it to Favre filtration, that what you arrive on the macroscopic level is exactly the Moch-Stadmer model. Okay, but we had to do one more thing. We had to modify one more time. Okay, and this creates another over-modified filtration. And what's interesting is that it has a lot of benefits. So in my book, I actually advocated quite extensively for the use of this particular filtration in various hydrodynamic limits. And in fact, that's the one that I used to improve on Figali and Kahn hydrodynamic limit result to flux with finite support. It restores symmetry to Moch-Stadmer equation, which was lacking. And it also actually is relevant to Ansager conjecture, believe it or not. In non-homogeneous Euler and Navier-Stokes equation, together with Trevor Leslie, we use this kind of modification, but in terms of Littlewood-Paley projections to approve sharp Ansager critical results for conservation laws, okay, for non-homogeneous incompressible fluids. So we're going to use this this alignment model in the context of Fokker-Planck, and what we arrive is actually a result which does not require any connectivity. Okay, so this is why it's so so powerful to this kind of point of view, so powerful, because the connectivity will be restored eventually, because the noise spreads flux around the torus and it will lift up the density eventually. But initially you don't even require that. All you need is the macroscopic velocity to be bounded. Okay, and that's just to ensure that you have a bounded averages here, so that your drift coming from the alignment term is a bounded field. So under this only assumption, you obtain relaxation to the global Maxwellian at an exponential rate, and you can actually trace down how it depends on the noise level. So that's a new theorem that I would like to present, and I will just give in the remaining, I don't know, 5-6 minutes of my talk. I will give just a few details how the proof goes. So you rewrite the Fokker-Planck equation using this Villani notation. So you actually work with the distributions. You renormalize your density distribution by global Maxwellian, and you arrive at this new equation. Of course, this, I mean, not new equation, but the same equation, but it has a new look. In some sense, it's much easier to work with this equation than the original one, because you work in weighted L2 spaces, weighted by Maxwellian, and somehow the operator algebra manipulations are very well suited for this setup. So your diffusion term is just A star A, where A is the gradient. A star in the weighted space has this form, and B is your spatial transport. And even the alignment term can be written in terms of this A operator. So what we're looking for is to establish, we establish convergence to Maxwellian through relative entropy method. So we look at the relative entropy, and we look at, because by Caesar-Kullback inequality, we know that it actually dominates the L1 difference between F and Maxwellian. Now, if you like if you write the entropy equality for entropy equation for this entropy, you see two different terms. One is the what's called the Fisher information. That comes from the classical Fokker-Planck, and the other one is the alignment energy. So the first term is very good. The second term is not, because it's not sign definite even. But even if it is sign definite, it's actually positive. Okay. So it kind of kicks you out of your relaxation dynamics, right? The alignment energy, it kicks you out from the monotonic convergence to the Maxwellian. But okay, but even without this energy, you still have a problem, because the Fisher information here is only in terms of kinetic variable. So it dominates relative entropy between your distribution and not the global, but local Maxwellian. So Maxwellian pre-weighted with the density. Okay, so it's time dependent. It's the macroscopic density of F. So on the one hand, the system pushes you towards the local Maxwellian, and the global is somewhere here. So there must be a mechanism of relaxing this local Maxwellian back to the global one. And of course, if you just studied this Fokker-Planck with the degenerate diffusion, that won't even happen, right? So what does happen is that the spatial transport term mixes up things between X variable and V variable. And this is, of course, a very known effect, goes back to the Kolmogorov and Hermander seminal papers on hyperellipticity. But dynamically, what it does is it basically uniformizes the macroscopic density to just a uniform state. So the local Maxwellian the dynamics goes back and forth between local Maxwellian and global. So it's not like a straightforward monotonic dynamics. So what happens is that now we have to compensate for the lack of diffusion in X variable, and that's what's done by the classical hyperellipticity estimates, hyperrecursivity. But we also need to deal with the alignment energy, and the way to deal with the alignment energy is, in fact, to discover another form of the entropy law, which is this here. Okay, this is actually a dissipative law, but it doesn't have any Fisher information anymore. And in order to have a coercivity of the alignment energy, I have to assume spectral gap condition on my average. So basically what it means is that this has to be less than a multiple of the energy itself. So in order for that to happen, I need to assume some kind of connectivity of the density. Okay, this is an unfortunate assumption, but it's only temporary. It's just to get this spectral gap. So basically, I'm assuming that the density convolution with the communication kernel is bounded from below. Okay, so with this tool at hand, we do gain both convergence to local Maxwellian and depletion of alignment energy. So now we have to combine it with the differential equation for the full Fisher energy, where we include all the mixed information and the information in X. And this is actually an idea that comes back to Villani. But as we write this equation for the full information, this is where the choice of that particular overfiltrated average plays a major role, because the two terms, the two parts of the equation really interact, and you have to hide the alignment, some junk that comes from the alignment part of the equation, into the dissipative term that comes from the kinetic linear Fokker-Planck equation. So in the end of the day, you obtain something like this, and then you kill the alignment energy with this form, second form of the entropy, and you arrive at Gromov. Okay, so eventually it will give you exponential decay of the relative entropy, and as a result, relaxation to Maxwellian. Now, but we need to get rid of the connectivity, because I told you in the beginning that's actually not interesting to assume that, and that is actually done through the noise. So the noise is working in such a way that it redistributes the flock, and the solution at some point of time gains global Gaussian lower bound. This result, this is a known effect. It comes back to Kolmogorov and Hermander, as I already said. For homogeneous Landau, it was done by De Villiers and Villani, Vlasov Fokker-Planck by Villani in his book. And then, but in our case, we had this extra drift term, but the drift, by our assumption, is bounded. Okay, that's where it enters into the proof. And because it's bounded, we can apply Harnack inequalities proved by Gauss, Imber, Mahon, and Vasseur relatively recently, to piece together several Harnack inequalities on the torus, kind of covering argument that gives you lower bound. So you have a bump at some point of time, and then you construct Gaussian barriers to actually gain Gaussian tails in kinetic direction. So at the end of the day, you do obtain, in fact, point-wise, not just convolution, but point-wise lower bound on the density, and that closes the argument. So the proof has many moving parts, but at the end of the day, you do reconnect and you do Maxwellize to uniform state. So there are many resources. If you're interested in this subject in general, there are many interesting resources. There are some older ones and there are some recent ones. There are survey papers which appeal more to describe how everything related to the real biological systems, very interesting reviews. And there are more mathematical ones by Moch and Tadmar, Singular Dynamics in this paper, and I also released a recent book where all these issues, except for hypercursivity, of course, because this is a recent development, all these things have been exposed in every detail. So if you're interested, you can check these sources out. And I think that's it. Thank you very much.
All right, let's thank Roman for this very informative and interesting talk. And now I think we are a little bit out of time, but if anyone wants to ask a quick question.
Sorry about that.
No, it's fine. Yes, Trevor.
Yeah, I have two quick questions. First of all, those simulations that you showed earlier, that you and Anil did, were those for metric or topological communication?
Metric singular.
Sure.
So completely local, metric and singular.
Got it. So, like you said, we saw something that looked sort of like close to locked states that you want to disrupt with this stochastic forcing. And it seems like analytically you're able to do that. Do do you have a feel for how long that takes? Whether you still expect that huge transient period of time before you actually see things
yes, of
align?
course. And in fact, this is already encoded into the rate of convergence.
Sure, that constant C1 is a big okay, I see.
The sigma, yeah, that's the one, right? This rate actually deteriorates as you let sigma go to 0. So when your noise is very, very weak, you will have a long transient period of locked states before they actually disperse.
Sure.
I think this rate is sharp. I think that I haven't done a careful scaling analysis, but I think it is sharp just from the scaling.
All right, thank you.
So because the poster session has started already, I think let's thank Roman again. But if anyone wants to stay here and ask more questions, I just wanted to maybe end the session just to give the opportunity for whoever wants to leave now. So let's thank Roman again for this nice talk.
Thank you.
And the poster session is starting now, and there should be a link on the chat, I believe. Yes. So just feel free to just click on that, and we'll resume here in at 2:30 Brazilian local time. See you later.